Good day to you. We're here in ESF's tropical greenhouse, and our topic today is leaf shape. The leaf of the higher plants has a very simple basic architecture. It's a flat sheet of photosynthetic tissue bolstered in a few places by the vascular structures that transport water in and export sugar out. On top of this rather simple structure, however, leaves come in a vast array of sizes and shapes, from tiny to immense, from simple in shape, or with serrated edges, or wavy edges, to deeply divided leaves like this one. How can we explain this? There are lots of reasons why a leaf might have a particular shape. Many leaves, for example, are tapered into elegant tips. Particularly for leaves in wet forests, these are often devices for channeling raindrops quickly off the leaf. A large part of the variation of leaf shape, however, and our focus today, has to do with leaf temperature. When sunlight shines on a leaf, it heats it up. If a leaf gets too hot, it may be unable to carry out its essential function of photosynthesis, so it has to be able to shed this excess heat somehow. This happens by the process of convection, by losing heat to air as it flows over the leaf. The leaf size and its shape have a lot to do with how effective this convection heat loss is, and therefore how much a leaf will heat up when it's exposed to light. And that's what we're going to look into today. So let's get started. Here's where we're going to do our measurements in one of the research greenhouses atop Illick Hall. We'll need three things to do our study: a light source to heat the leaf up, a source of wind to carry the heat away, and some way to measure leaf temperature. The light is going to come from these mercury vapor lamps mounted up here. We have them switched off at the moment because they make a terrific racket when they're on, but they put out light that's a reasonable imitation of the light coming from the sun. When they're switched on, it can get quite warm under them. Our wind is going to come from this little homemade wind tunnel right here. It's basically a desktop fan with a bit of sheet metal attached to it with duct tape. About the only high-tech thing about it is this transformer, which we use to make the propeller spin faster or slower. And inside the tunnel, we have this array of drinking straws glued together. The fancy name for this is the collimator. It basically straightens out any rotational movement the air might have due to the spinning of the propeller. It's pretty simple, but we can get wind speeds of up to about 2 meters per second from it. Temperature is a more challenging issue. We can't just stick a thermometer onto the leaf because that would likely affect the leaf temperature itself. So what we have is this device, which is a thermal imaging camera. This camera measures temperature by measuring the intensity of the infrared radiation that is emitted by any surface that is warmer than absolute zero. It focuses the infrared light through a special lens and makes an image, just like a regular digital camera does, but now the image is temperature. So we'll take a leaf, put it onto this net, which is basically a way to hold the leaf so that air can flow easily around it, shine the light on it, blow air over it, and take its temperature with a thermal imaging camera held rather precariously on this tripod. Okay, let's get busy.
Let's start with a simple problem. How does leaf size affect the leaf's temperature? We'll use some real leaves to explore this question, of course, but it will help to start with some ideal leaves for comparisons. So we'll also use some artificial leaves, basically sheets of metal cut out and painted black, as you see here. We'll first compare a small model leaf, 25 square centimeters in extent, against the larger leaf, which has 3 times the surface area. Surface area is important because the radiant heat absorbed depends upon it. Here are the infrared images of the two, mercury vapor lamps shining on them in still air, side by side. Red is hot and blue is cool. In still air, the large leaf is very clearly the hotter leaf. Let's see now what happens when we blow air over them. The wind comes from the top of the picture. They cool down clearly, but the temperature difference remains. This is with a wind speed of about 1 meter per second. Now let's boost the wind speed to 2 meters per second. Both leaves cool down still more, but the larger leaf is still the hotter one. Now you might be thinking, so what? Of course the big leaf will be hotter. It has 3 times the surface area and is absorbing 3 times the radiation heat. It's not that simple, though. Let's see why. Let's take a hypothetical leaf. How much heat should a leaf absorb from radiation? First and obviously, the more intense the light is, the more heat it should transmit to the leaf. That makes sense. Second is the absorptivity of the leaf. This is the opposite of reflectivity. The more reflective the leaf, the less heat it will absorb. That's also sensible. For our black model leaves, reflectivity is close to nil. Finally, there's the leaf surface area. We've already dealt with this one. The greater the leaf surface area, the more heat it will absorb. Our large leaf model has 3 times the surface area, so all other things being equal, it should absorb about 3 times the heat that the small leaf model does. So what's the problem? Remember, though, that leaf temperature is a heat balance, so that heat absorbed from radiation must equal heat lost by convection. How much should that be? Well, first, there must be some temperature difference between the leaf and air. The leaf won't lose heat unless it's warmer than the air. Second, there is a number called the convection coefficient. This is where wind effects, like wind speed, are taken into account. The larger the convection coefficient, the more easily heat is lost from the leaf, and the lower will be the leaf temperature needed to dump the heat absorbed. This is why leaves are cooler at higher wind speeds. Higher wind speeds reduce convection coefficients. Finally, there's leaf surface area, and here's the problem. The large model, with its large surface area, might be absorbing 3 times the heat, but it's also losing 3 times the heat by convection. This means that there should be no difference in temperature between the large and small leaf models. Yet there obviously is a difference. We observed it. What's going on? What's going on is an effective leaf size on the convection coefficient. Air flowing over a leaf forms a so-called boundary layer. This is basically a region of viscous momentum transfer from the wind to the leaf, but there's an additional effect. It impedes the loss of heat from the leaf by convection. The thicker the boundary layer, the smaller the convection coefficient will be, and the harder it will be for heat to be convected away by wind. Leaf size, leaf length specifically, affects the thickness of the boundary layer. The longer the leaf, the thicker the boundary layer will be. This is why, even though the larger model leaf has 3 times the surface area to dissipate heat by convection, the thicker boundary layer impedes it. The larger model leaf, therefore, must come to thermal equilibrium at a hotter temperature, which it does. This equilibrium temperature has a specific name. It is called the operative temperature, so called because it's the effective environmental temperature at which the leaf must operate. In any situation of radiation and convection, larger leaves will have higher operative temperatures than smaller leaves will. So far, we've only worked with model leaves. How about real leaves? Will they bear out this prediction? Let's find out. We'll look at 4 leaves that differ substantially in size. The smallest is from Pilia, the artillery plant, so named because of its habit of forcefully shooting its seeds from its flowers. Escianthus, named the lipstick plant because of its tubular red flowers. Spathiphyllum, commonly known as the peace lily. And Dieffenbachia, also known as dumb cane, because ingesting the sap causes intense pain and swelling of the tongue, rendering the victim unable to speak. They're all roughly the same shape, and their surface areas span about 3 orders of magnitude. And the Dieffenbachia leaf is about 30 times longer than the Pilia leaf. Let's look first at the leaf temperatures when there's no wind. Keep in mind that the air temperature in the greenhouse is regulated at about 20 degrees Celsius. Here's the temperature distribution for the smallest leaf, now for Escianthus, Spathiphyllum, and finally our big boy, Dieffenbachia. There's a clear effect of size on temperature. The larger the leaf, the more it's heated up by radiation. Note also how the largest leaf develops some pretty hot spots near its center. In nature, these are areas that could overheat and perhaps suffer damage. And what does wind do? We'll blow air past a leaf at about 2 meters per second. Here are the leaf temperatures for Pilia, then Escianthus, and Spathiphyllum, and finally Dieffenbachia. All the leaves cool down. That's to be expected. But here is the decline in average leaf temperature after turning on the fan. The smallest leaf cools the most when the fan is switched on. That's interesting. Apparently, the thinner boundary layers on the smaller leaves are disproportionately reduced by winds. So here is our first principle of leaf operative temperature. Large leaves are disproportionately affected by radiative heating. Small leaves are disproportionately affected by convection cooling. Okay, what about those variations of leaf shape? That's next. Let's begin, as we did with size, with some leaf models of different shapes. We'll use 4. Our small leaf with a smooth margin, one with a wavy margin, one with a pointy margin, and a lode model. All have surface areas of 25 square centimeters, so they'll all be absorbing the same amount of radiative heat. We'll make pairwise comparisons. Let's look at the model with the wavy margin first. When there's no wind, it's a tiny bit cooler than the model with the smooth margin. When we crank the wind up to 2 meters per second, both leaves cool, but the leaf with the wavy margin cools a bit more. How about the leaf with the pointy margin? Same story. The leaf with the complicated shape is slightly cooler than the one with the simple shape, in still air, as is the case here, and when they're exposed to wind. The temperature difference is really dramatic with the lode model, which is much cooler than the simple leaf, whether the air is still or blowing at 2 meters per second. Let's remind ourselves that each of these leaf models is intercepting the same radiative heating from the lamps. So what's going on? You won't be surprised to hear that it has something to do with convection. When air blows over a leaf, the boundary layer is not uniform in thickness. It grows. It's thin at the leaf's leading edge and gets thicker downstream. This means it's easier for a leaf to dump heat by convection from its margins, but becomes harder further downstream from the margin. This is why leaf temperature is slightly cooler along the margins than it is in the leaf center. Shape comes into the picture because changing a leaf's shape changes its amount of edge compared to its surface. We can quantify this by measuring the model's surface areas and their perimeters and taking their ratio. A large ratio means there is a high proportion of edge compared to surface. The wavy and pointy-edged leaves have slightly more edge than the smooth leaf does. The lobed leaf, on the other hand, has more than double the amount of edge compared to the smooth leaf. This is why the temperatures of the wavy and pointy-edged leaves are slightly cooler, but the lobed leaf is dramatically cooler than the smooth-edged leaf. Now how about real leaves? Let's compare two large leaves. One is the large smooth margin leaf of Dieffenbachia, which we've already encountered. The other is a strongly divided large leaf of the ornamental plant Monstera. If we look at their temperatures, the leaf with the more edge is clearly cooler in both still air and in wind. What is remarkable about this effect is that it doesn't really matter where the edge is. Here are two leaves of another species of Monstera. The leaves of these plants frequently open up holes in the middle of the leaf as it matures. We're still increasing the edge to surface ratio here, but now we're putting the edge not on the margins, but in the middle of the leaf. Are these edgier leaves cooler, even though their edges are in the middle? Yes, they are.
Okay, that was hot work. Let's review what we've learned. First, we learned that leaf temperature is a result of a heat balance between radiation heat absorbed and heat carried away by convection. When the heat budget is at equilibrium, the leaf temperature stabilizes at what is called the operative temperature. Operative temperature is the effective environmental temperature for the leaf. Second, we learned that large leaves generally have higher operative temperatures than small leaves do, mostly because large leaves have thicker boundary layers over them, which makes it harder for the leaf to lose heat by convection. The leaf's heat budget, therefore, must come to equilibrium at a higher temperature. In practice, this means that large leaves are more likely to be found in comparatively shady environments, whereas small leaves will do fine in full sun. Finally, we learned that leaf shape can affect leaf operative temperature in some complicated ways. Making a leaf edgier, for example, by having serrated or wavy margins, or making the leaf highly lobulated, will keep boundary layers thin, enhance heat conduction to the margins, and reduce leaf operative temperature. Okay, that's all for now. Until we meet again, this is Scott Turner wishing you a good day.